So welcome to the next lecture of advanced models in system biology, and we are still thinking about bistable systems. And bistable systems, as we've seen before, they have a bifurcation diagram that typically can be decomposed in these three regions, right? Where there's one region with one steady state and there's another region with one steady state, and in between there's a region with three. In some cases you can have this example where you have these irreversible transitions, whereas as soon as the system is up the higher branch of steady states, they can never return to the lower branch, because there is no parameter change that would bring them back, at least not of this parameter, maybe of another one. Okay, and there is one typical aspect of bistability that we haven't really thought about yet, and that's this curious effect that happens at these bifurcation points, or at these critical values of the parameters, right? Because what we see there is that at PC and PC prime, the derivative of x with respect to PC, with respect to P, is infinity, right? So here, when you move it back, you have this infinite slope, and here you have, when you move the parameter up, you also have this infinite slope. So there's something really curious going on. And we want to understand a little bit better what the conditions are for this infinite parameter sensitivity. So at bifurcation points, of bistable systems, infinite parameter sensitivity occurs. So if we define parameter sensitivity, the sensitivity of the system with respect to a parameter, as the change of a system property of this system, so at steady state, any steady state concentration or function thereof, right, is a system property. That means in principle, all the kinetic parameters of your model determine it. So that makes it a system property. So the steady state concentration of X is determined by all these kinetic properties of the network, so it's a system property. And at these bifurcation points, there is an infinite sensitivity of X with respect to the parameter, right? Because the slope is infinite, right? In this case it's negative, in this case it's positive. If you go down, it's negative, go up, it's positive. Alright, so actually also if you go down it's positive, because X decreases and you also decrease the parameter. So in both cases the ratio of this value and that value is going to be positive, and it's going to be equal to infinity. Alright, so we want to understand this. So we need to think about this now a bit more theoretically. So we know that in this particular case, we were thinking initially about this single variable system that had two rates. Now we know that these two rates depend on the concentration of X itself, right? And if we think about a parameter that we're going to vary along this axis in value, right? Then this parameter either occurs in rate equation 1, yeah, or it occurs in rate equation 2, right? So if it occurs in 1, then you could write something like this, right? So you know that the concentration that the rate not only depends on x but also on this parameter value. But if you write it like this, you overlook one thing. Okay, so this is the concentration at one particular moment in time. Okay, but this equally well depends on this parameter value, because if I would compare two systems that are the same in every feature except for the parameter value of parameter p, so they have the same initial conditions, everything is the same. If we compare these two systems, so x is function of time, so let's say this goes like this, it has parameter value p, and the other system has parameter value p prime. It has the same initial condition, but of course its dynamics will be different. Because at every moment in time, p will have a different value, so therefore v1 will be different for the same values of x, right? So these curves cannot be the same. So that means also that x is a function of p, and you get this. Because if I would compare two systems, one with value for parameter p equal to p itself, and the other one to p prime, so let's say value 3 and value 5, and everything else is the same, so all the other kinetic parameters the same and the initial condition, then the dynamics of x will be different, because already at the starting value of x, v1 will have a different value in these two systems. Okay, so the dependency of the dynamics of x on p has this functional relationship. Okay, so that means at steady state, where the concentration of x equals its steady state value, we have this functional dependency. If x occurs in the, if x is a parameter, if p is a parameter of the first equation, and clearly we would have this functional dependency if the parameter would only influence the second rate, right? Okay? So let's say we have this scenario and the system is bistable. So we know that there is a parameter value, these critical values of p, where the derivative of the steady state concentration with respect to p is infinite. Okay? And what we would like to do, we would like to understand these conditions. So we have to determine delta x, delta p, right? What it is, and identify when it is infinite. Okay, so that means we have to differentiate this system with respect to p. Okay, so how does that go? Oh, that's 1, 2. So you just use the rules of differentiation, and then you get this, okay? So that means that if we look at two systems, one at a certain value of p and the other one is just slightly the perturbed value of p, okay, then the difference between these two systems is given by this equation. Okay? So the system with the slightly perturbed value of p has a slightly different value of v1 because it has a slightly different value of x at steady state. But it also has a slightly different value of v1 because it has a slightly different value of p of steady state, because this is the functional dependence. And it also has a slightly different value of v2 at steady state, because the steady state concentration of x has been changed slightly due to the slight change in the parameter. Now, so that means I can solve for the derivative, this guy, that I'm interested in, right? So it turns out now, so let's write that here, that the sensitivity of the steady state concentration of x with respect to the parameter is given by the sensitivity of the rate with respect to the parameter, so this derivative, and the sensitivity of the rate with respect to x, and the sensitivity of the rate of v1 with respect to x, and v2 with respect to x. Okay. So we need to, and all these derivatives, okay, all these derivatives are evaluated at the steady state value of x. Right? So this is at a steady state value of x given a parameter value p. This is at a steady state value of x given that value of p. And this is also at x given that value of p. So these are all numbers, right? Okay. Now what we've already seen is that this difference, okay, that's the eigenvalue. So if you look back in your notes, you'll see is that the difference between the sensitivity of rate 1 with respect to xs and rate 2 with respect to xs, this difference is the eigenvalue itself will determine the stability. So when the system is stable, it's going to be negative, right? But now you also see, when is now this derivative infinite, okay, so delta equals infinity if lambda equals 0. Or when this other derivative equals infinity, but this generally doesn't happen. This will occur when the eigenvalue equals 0. So at these points, the eigenvalue has to equal 0. So that means it shifts in sign. Right? Because something equals 0, so when you have lambda as function of this parameter value, then first, if the steady state, so here you have negative values and positive values, if you increase the parameter value and the system is stable, then there will be some point where the system becomes unstable, and this is where the parameter it starts to have a positive value, right? Where the eigenvalue starts to get a positive value. And at the point where lambda is 0, you have the bifurcation point. Because this is where the system loses stability. In fact, this is exactly the system, the point where this steady state, right, becomes unstable, right? It's better to look at it from this perspective. So first it's stable, 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 stable. Then the steady state becomes unstable all of a sudden. So here you have a transition from lambda, so first lambda is negative, and here it becomes 0, and then it becomes positive. So here lambda negative, lambda positive. Then you further increase the parameter, right? And here there's this other transition where the steady state suddenly disappears. And that's also a bifurcation point, and that's also where the eigenvalue equals 0. Okay, so what we have now identified is that these weird sort of S-shaped curves, The curve, this is S-shaped because it has these infinite sensitivities, because alternatively, if the system would just be, let's say, sigmoidal, you don't have these infinite sensitivities, right? You can have high sensitivity, but not infinite. It only becomes infinite if it starts to look like an S-curve. And then there are these 2 points of infinite sensitivities. This is where qualitative changes in the behavior of the system occurs, because the number of steady state changes, and in this case also their stability. Now, it turns out that the conditions for infinite sensitivities is when the eigenvalue equals 0. That's what this computation tells us. So this is exactly the point where the system either gains stability, so the steady state becomes stable or becomes unstable, or it disappears. So these bifurcation points are characterized by eigenvalues of 0. So if you want to compute these bifurcation points, therefore you have to figure out the value of the parameter at which this parameter sensitivity is infinite. And you will then find 2 values, PC and PC. Okay, so that was the last aspect of bistable systems, at least for the one variable case. So that means that we've now finished section 13.6. Okay, I hope that was clear. Thank you very much.